Guy Barrett teaches this Docker Containers and Kubernetes Fundamentals course for beginners. Guy is a developer and trainer with more than 25 years of experience. He is a Microsoft MVP, frequent conference speaker, and was the leader of the Montreal.net user group for more than 23 years. All this is to say, he is the perfect person to teach you about Docker and Kubernetes.
Welcome to this Docker Containers and Kubernetes Fundamentals training course. My name is Guy Barrett, and I'll be your host in your learning journey into the amazing world of containers. I'm a full-time trainer with a developer background, and I'm based in Montreal, Canada, and that's where my strange accent comes from. I'm certified on Kubernetes and also on Terraform, Azure, AWS, and Google Cloud. I'm very honored to be a Microsoft MVP in the Azure expertise and a DigitalOcean navigator. You can reach me via the contact page and on Twitter. What should you expect from this course? You will not become an expert just by taking this course. This is an entry-level course that will provide you with a strong containers and Kubernetes foundation, and you'll gain enough knowledge to make sound decisions at work or in your projects. Throughout this course, you will find lots of hands-on activities to practice what you've learned. You will use Docker and Kubernetes locally on your PC or Mac, so there's no requirement to have an account with a cloud provider. Are there any prerequisites for this course? Not really. If you're a developer, a DevOps specialist, an IT pro, or even a technical manager, that's totally fine. No previous Docker or Kubernetes knowledge is required. We will cover a lot of ground. You will learn about containers, Docker, and the Docker registry. You'll learn about the Kubernetes objects like pods, workloads, and services. That's a lot of material, and the goal here is to get you from zero knowledge to a Kubernetes ninja. Well, at least provide you with enough knowledge to aspire being a Kubernetes ninja. I want to say a big thank you for learning Docker and Kubernetes using this course. If you like the course, you can help me by making a small donation. This is the link to my Buy Me a Coffee page. You can of course buy one of my other courses where you'll learn to run containers on different cloud providers' services and use a managed Kubernetes cluster in the cloud. And finally, I wish you all the best in your learning journey. Let's see how to set up your laptop or PC for this course. You need a laptop, PC or Mac, with either Windows 10, Mac OS, or Linux. If you have a Mac with an Apple Silicon, most tools should run perfectly. I will use Visual Studio Code with the Docker extension to help build, create, and run containers. VS Code is a free IDE that runs on Windows, Mac, and Linux. On Windows and Mac, you'll need Docker Desktop with Kubernetes enabled. On Linux, refer to the documentation on how to install Docker and Kubernetes on your distro. You'll need a Docker Hub account and a few easy-to-install tools. Refer to the setup instructions located below this video. The lab files are located in a Git repo on GitHub. Simply open this URL in a browser. Click on the Code button. If you have Git installed on your machine, you can type git clone with the link displayed here. And if you don't have Git, simply click on the Download Zip button to download the code as a zip file. Let's talk about the microservices concepts. If we head to Wikipedia and take a look at the definition that we find over there, it says that it's a variant of the service-oriented architecture, or SOA, a structural style / architecture, and that it arranges an application as a collection of loosely coupled services. So instead of a large monolithic system, we have multiple smaller pieces. In a microservices architecture, services are fine-grained, meaning that each of them have their own responsibilities, and the protocol used are lightweight, like an API exposed over HTTP or gRPC, for example. If we look at the monolithic architecture, these systems were usually built as one single unit. An IDE would group multiple projects, and we would compile the whole thing as one single unit. They were also deployed as a single unit, so we would need to copy everything, all the files on a server. And if we had to scale the system, we had to spin a new VM and deploy the whole system on that VM, and same for a third and a fourth server. An example of such a monolithic architecture is a three-tier application. Even though the system was clearly separated into layers, it was all tightly coupled. From the web project, we had to make a reference to the business layer project, and the whole system would run in the same address space. With microservices, we break our big system into smaller parts, each with its own responsibility. So let's say we have a class that deals with identity in our business layer. We can extract that code and place it in its own microservice. We can then scale each of these smaller pieces independently from each other. There's no strong bound since we expose functionality through an API. They can be written by smaller teams, and each can use their own programming languages like Go, PHP, C#. And domain-specific data can be stored in separate databases. So the way we would deploy a monolithic system is by deploying everything on a server, all the DLLs, files needed to run the system. We had to scale, deploy everything on more servers. Now let's compare that to microservices. Well, microservices are deployed independently. Each can scale independently also. Need to scale back one service? No problem. So if you have an existing monolithic system, how can you transform it into a microservices architecture? Well, you need to break it into small units, like the code that dealt with the identity in our business layer. Martin Fowler, author of the Patterns of Enterprise Application Architecture book, documented a way to achieve such a transformation using the strangler pattern. Let's say our identity code is here in the legacy system. We can place a facade to route the calls to it, migrate the code, and have the facade route the calls to the new microservice at some point. As we go, we will end up with less code in our legacy system, and when the migration is done, we can get rid of the facade. This pattern is very useful, and you can learn more about it using the link in this slide. And this concludes this lecture on the microservices concepts. Let's talk about microservices anti-pattern, because it's not all rosy. I know, It's kind of strange to talk about what can go wrong right away, but I think it's very important. First of all, it's not some kind of magic pixie dust that you can sprinkle on top of an existing system and boom, you get a beautiful microservices architect system. It takes efforts and maturity to achieve this. From one monolithic system, you'll end up with a bunch of smaller pieces, and that can add extra complexity. A change to a microservice can have a domino effect and take your system down. And what about securing all of these microservices? It's also essential to use or introduce new processes in the organization, like DevOps, CI/CD, and testing. But be careful and don't try to implement everything at the same time. It's a recipe for disaster. Take it step by step and make sure you have metrics in place to validate each of these steps. And this concludes this lecture on microservices anti-patterns. Let's talk about the microservices benefits and drawbacks. Since each microservice runs in its own address space, there are less chances that if one of them goes down, it takes the whole system down with it. A microservice runs on open source technologies, so there's less vendor lock-in. Since they are smaller, in most cases, they are easier to understand, and that makes them faster to deploy, and also easier to scale. Like we saw in the anti-patterns section, there are some drawbacks. Complexity is added over monolithic systems to resolve their complexity issues. So make sure your team is well trained and has made some proof of concept, and make sure to start small, adding one piece at a time. Testing might appear simpler since there are less functionality in a microservice to test, but make sure to test the whole system. Deployment may appear simpler, but one update can impact many microservices and have a terrible domino effect. Ready to manage multiple databases? Calls between microservices will go through APIs, and this will add a bit of latency to all calls, so make sure you test for that. Pesky transients error will appear. You'll make a call, and it will fail, but try again 50 milliseconds later, and it will work. So make sure to implement some retry strategies in your code or by using a service mesh. Instead of one big point of failure, you'll end up with multiple ones. Can your system survive if one microservice goes down? And what about security? Are you okay if all these microservices can see and talk to each other? So yes, complexity is introduced for solving complexity issues. And this concludes this lecture on the microservices benefits and drawbacks. Let's now understand what is cloud native. You may have heard the term cloud native before, but what it is exactly? It's a way to architect and build complex systems, taking advantage of modern development practices and the use of cloud infrastructure. If we head to the Cloud Native Foundation website and look at the definition, we see that it's quite a long one. So let's break it into smaller parts. Cloud Native uses containers, service meshes, microservices, immutable infrastructure, and declarative APIs. We'll cover containers, service meshes, and microservices and the concept of immutability in this course, but not how to build APIs. Immutable infrastructure means that we usually never update something, but we replace it with a newer version. Loosely coupled systems mean that the functionalities are exposed through APIs. Observable with the use of metrics. Creation and updates are automated. And instead of making changes once every 6 months, we deploy high-impact changes on a frequent basis. And finally, we use a series of open-source projects to run our system. When the CNCF says to use open-source projects, they are not kidding. This CNCF landscape graph shows a ton of open-source projects that you can use, but don't worry, you don't have to use them all. The challenge really is to identify which one to use in the context of what you want and try to achieve. And this concludes this lecture on Cloud Native. Head to the CNCF website for more info. Let's go deeper in the Cloud Native concepts. Cloud Native is about speed and agility. The user wants new features right away, without any downtime. And the business wants faster release of feature to stay competitive. A cloud-native application architecture starts with clean code. Using domain-driven design techniques, microservices, and Kubernetes. This course is all about microservices and Kubernetes. Feel free to explore the concepts of clean code and DDD on your own. With Cloud Native, we need to change mentalities. Infrastructure becomes immutable and disposable. It is provisioned in minutes and destroyed as fast. It is never updated, but it's replaced with newer versions. Traditionally, we would care about our virtual machines. We would patch the OS, update the apps. With containers, we create newer version with the software updates, destroy the previous running ones, and replace them with the newer ones. So the containers that you'll run will be more like cattle than pet. Of course, this cloud-native thing is a lot easier when starting a new project, a blank page or a greenfield. However, it's still possible with legacy projects. I really like the Cloud Native Foundation Trail Map because it breaks the journey to Cloud Native into smaller, measurable objectives. You can set your own performance indicator to measure each steps to ensure a smooth journey. So let's take a look at the first steps. Your team must first learn how to containerize your application. The developers and the IT pros must know how to deploy and monitor containers. You need to automate deployment through the use of continuous integration and continuous delivery techniques and tools. You need to use an orchestrator like Kubernetes and maybe deploy your application using Helm charts. Then you need to add observability so you can understand what's happening in your Kubernetes clusters and be reactive. Use tools like service meshes to provide more functionalities inside your cluster. Implement security through policies. And wow, these were just the first 6 steps. Now, understand that you don't have to implement all of this, and especially not at the same time. I really like this trail map because it breaks the journey into smaller steps that the management can understand and measure. And this concludes this lecture on the cloud native concepts. Let's take a look at the CNCF website. The website is located at cncf.io. And from there, you can take a look at the various projects maintained by the CNCF, information on how to get certified, community information like the conferences that the CNCF organize each year. So let's go back to the projects menu. And you'll notice that projects are categorized in 3 categories: sandbox, incubating, and graduated. Let's click here on this, the second menu here. And let's scroll down to the bottom. And here you get the information about the meaning of these 3 categories. And basically, that's their maturity level. Sandbox projects are mostly newer projects, while graduated projects are projects that conservative enterprises are more likely to use. So let's take a look at the graduated ones. We found here Kubernetes, Helm, Jaeger. So let's click on Kubernetes. And basically that will show you the project website. Let's take a look at the incubating ones. Here we find Linkerd, gRPC. Let's click on gRPC. You can get more information about the gRPC. All right, let's go back to this menu. Remember the trail map that I mentioned in the previous lecture? Well, here it is, Cloud Native Trail Map. Here's the nice diagram. You can get more information. You can send that to friends, colleagues. And here's a link to the landscape diagram. Here it is. It's super huge. Let's click here on Kubernetes. And here you get very interesting information. Well, you get the repository where the project is stored. You get the number of stars and the activity number of commits here. You get the website address and also the Twitter handle here. So you should follow the Twitter feed of the project that you are using. So let's close this one. Let's click here on Helm. Again, website, repository, number of stars, activity, and the Twitter handle. And this concludes this look at the CNCF website. Let's now talk about the containers concepts. Containers, containers, containers. They are everywhere, but what are they exactly? A container is a unit of deployment. It contains everything needed for the code to run. So the compiled code, the runtime, system libraries, and the system tools. You take a container, push it on a server, and it should run. Of course, it can have some external dependencies like a database or a cache, but the code deployed in it should run as is. So why use containers? Because it is faster to deploy something small than something big, like a complete monolithic system. They use fewer resources, they are smaller. And since they are smaller, you can fit more on the same server. When using CI/CD techniques, they are a lot faster to deploy. You can run them anywhere. And they are isolated from each other, meaning that if one fails, it will not take the whole system down with it. So what exactly is virtualize? Let's compare virtual machines with containers. A VM runs on some kind of hardware where an OS is installed. The OS hypervisor will let you create a virtual machine where you will install an OS. So basically, the VM virtualizes the hardware. And what's happening when a VM starts? Well, you see the BIOS coming up, and then the OS boots up. And what about the size of that VM? Let's say we have a Windows Server VM. It can take 12 gigabytes of RAM and 500 gigabytes of hard drive space. And how long does it take to boot? Well, depending on multiple factors, something like 5 to 10 minutes. Now, let's compare that to containers. We still have the hardware and the OS, of course. There's a container runtime installed in the OS, and containers images are run in memory. Now, compared to a VM, a container does not have to boot because it will use the host OS kernel. This means that container starts in seconds because they don't have to boot. They also use a lot less memory and hard drive space since there's no OS. A small container can take 100 megabyte of hard drive space and run in 64 or 100 megabyte of RAM. So, VM and containers. Virtual machines have a larger footprint. They are slower to boot. Ideal for long-running tasks. Containers are lightweight. They're quick to start. They don't have to boot. They're portable. And they're ideal for short-lived tasks because you can spin one super fast. So, are containers replacing virtual machines? Are virtual machines obsolete? Absolutely no. Containers are just another tool in your toolbox, and you need to find the right use case for them, and also for VMs. If you're old enough, you must remember what the telephone boot is. If not, well, before cell phones, we used to make phone calls in these booths by dropping a dime or a quarter. Anyways, using a telephone boot analogy, you can pack more containers on the same server than what's possible with virtual machines. Containers are made of layers. You start with the base OS, add customizations, and add your applications. Let's take a deeper look at this screenshot. The Docker pull command retrieves and downloads a container image. As you can see, each layer is downloaded individually. Notice that each has a unique ID, and that for the first ones, Docker says that they already exist. Why is so? Docker uses a local cache to store the container's images, and if a layer already exists, it will not be downloaded again. The benefit is that if you pull version 2 of an image, Docker will only download the layers not present in its cache. One of the goals when creating container images is to create them with the smallest number of layers possible. Later on, we'll see techniques on how to achieve that. Now, can you write on these layers? Well, no, except for the top one, because it is read-write. The lower ones are read-only. Another concept is the container registry. It's a centralized repository where you deploy the container images you create. Think GitHub, but for containers. Docker has one called Docker Hub that provides public and private repositories. And all major cloud providers have container registry services. The last container concept is the orchestrator. An orchestrator allows us to manage, scale, monitor the containers that we run on our servers. You can install your own or use a managed cluster offered by one of the cloud providers like AWS, Azure, Google Cloud. We will come back to the orchestrator concepts after we have a better knowledge of containers. And this concludes this lecture on the containers concepts. Let's now understand what is Docker. So, what is Docker? That may seem like a simple question, but there's more to it. There's Docker the company and Docker the platform. Docker maintains the Moby project, an open source container runtime that follows the specs from the Open Container Initiative. Docker sold its Docker Enterprise Division late 2019 to a company called Mirantis. So if you want to buy enterprise support or get certified with Docker, you have to go through Mirantis. Docker provides a container runtime that runs on Mac, Windows, and Linux, a command line tool to create and manage containers, a Docker file format for building containers, and interestingly, Windows lets you create both Windows and Linux containers. A quick tip. If for some reason Docker doesn't seem to work on your machine, try restarting it by using the Restart menu from the system icon on Windows, or by clicking on the debug icon in Docker Desktop on Mac and Windows, and clicking on Restart. Docker Desktop is very stable, but I had some issues when my laptop was coming back from hibernation, but that was a long time ago, and I haven't had issues for a while. And this concludes this lecture on Docker. The easiest way to run Docker on your machine is by running Docker Desktop. It's a free download available on docker.com. So you click here on Get Started, and you download the version for your OS. So Windows, Mac, Linux here. Now, if you're running Windows, check the version of Windows that you're running. If you're running Windows 10 version 2004 or a later version, you can run what's called Windows Subsystem for Linux version 2. So WSL2. Basically, it allows you to run a Linux distribution right into your Windows installation. So Docker Desktop can run its container by installing a virtual machine inside Hyper-V, or if you have WSL2 installed, it will install that virtual machine inside the Linux distribution, and everything will be a lot faster. So that's the preferred way. So just to prove a point here, I'm going to launch my Hyper-V Manager. And as you can see, I'm not running any virtual machine. So my Docker Desktop installation uses WSL2. You'll find a link to this installation guide in the modules notes. Okay, so let's take a look at the Docker Desktop. I'm running Windows. As you can see, I can see my Docker Desktop system tray icon here. So for Mac user, it will be at the top of the screen, of course. I can right click on it and let's select Dashboard. All right. So here I can see a list of containers that are currently running. I can stop them, restart them, delete them. I can see a list of images that are installed on my machine here. We'll come back to that later on. There's a gear icon here. That's the setting icon. And in the general section here, you can see that WSL2 is enabled. So that's why Docker Desktop doesn't use an Hyper-V virtual machine. It uses the WSL2 to run the VM. And there's the Kubernetes menu here. If I select it, I can see that Kubernetes is enabled. So when you check that, Docker Desktop will download additional containers to run Kubernetes right onto Docker Desktop here. So very useful. There's a bug icon here, which is the troubleshoot icon here. So if at some point you're issuing Docker commands and they don't work or something's wrong running Docker commands, you can click here on the restart button here. You can see my name here. It means that I'm currently logged. And if I right click down on the system tray icon, you can see that I'm currently logged in and I have the option to sign out. So what username and password did I use to log in? When you downloaded the Docker Desktop, you could have created a Docker account or a Docker Hub account. So that's the same username and password. So if you go to hub.docker.com and you logged in, well, that's the same account that is used here in Docker Desktop. Let's take a look at your first Docker CLI commands. Now, throughout this course, I will introduce you to various commands. I will list them in what I call a cheat sheet list, like what you find on this slide. I will briefly explain what the commands are for, and that will be followed by a concrete hands-on demonstration. So when you install Docker Desktop on your Mac or PC, it also installs the Docker CLI tool. Our first command is docker info. This will display some information about the Docker installation on your machine. Docker version will display its version. And Docker login will log you into a Docker registry. By default, this login command will log you into Docker Hub, the registry from Docker. And this concludes this lecture on the Docker CLI. All right, we need to open a new terminal window into Visual Studio Code. So let's select a terminal, new terminal, or you can use the shortcut Control-Shift-Backtick key. All right, this will open a terminal window. And let's take a look at the commands that we will run. They're really basic. It's just for testing that our Docker installation is working correctly. So let's type docker info. This will give me some information about my current installation, what's happening. I have 47 containers, 3 stop, 44 running, 25 images, and so on and so on. So information that is quite useful for debugging purposes. I can see that the virtual machine running Docker Desktop is running has 2 CPU. It has 2 gigabytes of memory allocated. All right, sounds good. Let's type now Docker version. And this will give me some information about the version number of different parts of Docker Desktop. So again, useful for debugging purposes. These are not commands that you will run on a day-to-day basis, but they're quite useful for troubleshooting. The last command is docker login. So I'm just going to type docker login without any username password, see what's happening. And well, the command says that I log in successfully. Why so? Well, if I right click here on my Docker Desktop, I can see that I'm already logged in. So that's why I didn't have to input or type any username password. I was already logged in. Let's now see how to run containers. The docker pull command lets you download an image from a registry. Docker run will execute an image in memory as a container. If the image is not present in the Docker local cache, it will be downloaded automatically. Using run with the -d flag will run the container in the background, giving you your command prompt or terminal back. The start command will run a container in the stopped state. Docker ps will list all the containers currently running and add the -a flag to also list all the stopped ones. Docker stop will stop a container running, but the container will still be in memory. We will see how to remove them from memory in a few minutes. Docker kill will, kill a container that might be stuck in memory. You usually don't use this command, but it's useful to know. Docker image inspect will give you some information about an image, very useful for debugging purposes. So you may notice that we have two parameters here. One is called image name and the second one container name. So what's the difference? The image name is the name of the image as you find it in the container registry, and the container name is the name of the running container. So you run an image using its name and then interact with it using the running instance name. The run command has an optional flag called --name that lets you specify a name. If you don't specify one, Docker will auto-generate one for you. You can set limits on the memory and the CPU that the container can use when using the run command. So how do you run a container? Using the docker run command, you specify the image name as found in the container registry. You specify a name for the running instance. And with the publish flag, you map a port from your local host to the port that the container is listening to. You can list the running containers using Docker ps. Notice how we stop the container by using the running name and not by using the image name. Then we remove it from memory using the remove or rm command. Containers are not black boxes. You can attach a shell to your terminal and run commands that will execute right inside the running container by using the -it switch and the name of the program you want to run. Running a Windows container? Well, you can run PowerShell. Using the docker container exec command, you can attach to a running container. Here's a screenshot showing the docker run command. And notice the terminal prompt changing when attached to a container. So how do we clean up things? The remove command lets you remove a container from memory. But first, it must be in the stop state for the command to work. Here's the remove command getting a list of the stopped container and removing them all. The images that you pull will be cached locally. You can get a list of these images using the docker images command. Use the remove image or RMI command to delete an image from your machine. After a while, you may end up with a bunch of images. To do some spring cleanup, use the system prune command. This will delete all the image currently not in use, so be careful using this command. And this concludes this lecture on the Docker CLI. Let's now run our first container. We'll run an Nginx web server, so something pretty basic. That'll be perfect for this lab. All right, let's open a terminal. So terminal, new terminal, or Control-Shift backtick. Perfect. So we'll run this command. So let's take a look at the command first. So we'll run a Docker run, and let's go at the end of the command. This will be the image that we'll run. So an Nginx image. We'll give it a name. So the name will be web server. That will be the name of the running instance. We'll map local host port 8080 to the port that the container is listening to. So port 80. And -D for detached mode, so we can get our command prompt or terminal prompt back. So let's run this. Something interesting is happening. Unable to find image Nginx latest, and you see that Docker has pulled all the different layers locally here. So now, if I issue a Docker PS, it will list the containers that are currently running. So I have 3 containers running. So the Kubernetes dashboard and the metric server here. So don't look at these. Let's focus on this one. So this is the containers that we just launched, the Nginx image here. It started 30 seconds ago. We can see that port 8080 localhost is mapped to the port 80 here, and the name is web server. So let's launch a web browser, and let's type localhost 8080. The container is actually running. Fantastic. All right. So we can get a list of the images installed on your machine here by using Docker images. So I have a bunch. I may have a lot more than you, but let's focus on the last one here. Nginx, the tag is latest, image ID, and this is the size. All right, fantastic. Let's try to connect to it. So we'll issue a Docker container exec. We'll give it the name, so the running instance, and the program we want to run. So look at the prompt now. Root at some ID. So the ID is the actual container ID. So I'm logged in as root on that container. So now I can issue some commands. So let's do an ls. Let's type ls bin to see what's in there. So different commands. So I'm connected to that running container. That's pretty cool. So I can issue commands, look at the logs, if any, and do some troubleshooting. So this is super useful for debugging purposes. We'll use that a lot in the various labs that we'll do together. All right, let's get out of there by typing exit. All right, just clear my screen here. So our container is running. How do we stop it? We use the Docker stop command, but look at the parameter that we use, the name of the container that we use. We use the running instance name, not the name of the image. So that's pretty important here. Docker stop web server. All right, but the container is still in memory. If I do a Docker PS, it's not listed anymore as a running container, but if I type Docker PS dash A. Aha, for all, I can see that my container is still in memory here. So I need to remove it from memory. So we'll use the docker rm and the name of the running instance. So rm for remove. And now the container is no longer in memory. Awesome. Now, the container is still, well, the image that was used to create the container is still on my machine. So if I type docker images, you see it's still here. So that takes 133 megabyte of disk space. If I want to get rid of that, I use the RMI, so remove image command, and the name this time of the image, not the name of the running instance, because none are running right now. And you see all the layers have been deleted. Let's now see how we can build containers. Docker build lets you create an image using a Docker file. If you run the command in the same folder where the Docker file is located, simply use a dot as the file name. If the file is located in a different folder, specify the location using the F flag. The tag command lets you assign a name to an image. This tagging has two parts, a name and a tag. The tag is usually used to specify the version number. So, what is a Docker file? Well, it's a text file listing the steps to build an image. Here's the simplest Docker file I can imagine. 2 lines. The from command specifies the base image. When building new images, you always start from something already existing. In this case, an image with the Nginx web server using the Alpine version. And then the copy command copies everything from the current folder to a folder inside the container. Using the build command, we create a new image specifying the Docker file. Remember to use the dot when the file is located in the same folder. Here's another one, this time a little bit more complex. It is used to create an image running a Node.js app. Let's take a look at it. The from command specifies the base image. Using the run command, we run the package manager inside the container to install Node.js. Next, we copy all the local files into a folder named src inside the container. We use the run command to do an npm install. We then add some metadata. In this case, we tell the container to listen on port 8080. And finally, we tell the container what to run when starting. So, as you see, this Docker file contains the steps needed to run our Node.js app. We saw what tagging was a moment ago. Let's explore this again. Using the docker tag command, we name an image using a name and optionally a tag. If you don't specify a repository name, it will default to Docker Hub. Later on, we'll see how to push images to different repositories, and we'll have to specify the repository name when tagging our images. And this concludes this lecture on how to create Docker images. Let's see how can Visual Studio Code help us build and run containers. So what is Visual Studio Code and why talk about this tool in this course? Well, it's a text and code editor. It's free and open source. It runs on Windows, Mac, and Linux. And you can download it for free using this link. So it will work a lot with text files, creating Docker files, and later on Docker Compose and YAML files. A tool like VS Code will help you because you can install plugins that will make your life easier. Using a different text editor? No problem. In VS Code, you can install plugins by clicking on the extension icon in the left menu. Then you search for Docker and install the extension from Microsoft. The extension lets you add Docker files to your projects using the command palette. Open it using the View menu or type Ctrl-Shift-P. Type Docker add and select Add Docker files to Workspace. The extension will ask you a few questions and will create the Docker files for you. VS Code has a built-in terminal where you can type commands, or you can run commands using the command palette. Here's another example when running a container. And when using the command palette, there's no magic there. The extension will simply issue a command in the terminal. But sometimes it's a great way to learn. Creating Docker files is okay, but what I like the most is the UI provided by the extension, helping me manage my container. So if you click on the Docker icon, you can see the images installed on your computer. And you can even see the containers currently running. Right-click on an image to manage it. Same thing for the containers currently running. Very, very, very useful. And this concludes this lecture on VS Code. Let's now use Visual Studio Code to containerize a Node.js Express application. So I already installed the Docker extension in Visual Studio Code, but let's take a look at it. So if I click here on extensions, and let's search for Docker, here it is. That's the one from Microsoft, almost 6 million install at the time of recording. So that's the one. All right, so let's go back to our files. So I have my Node.js application here. If I click here on package.json, the name of my application is my Express app. So that'll be important in a few seconds. All right, so let's first add the Docker file to our project. So we'll use the tooling provided by the extension to do that. We'll go to the View menu, Command Palette, or you can use the shortcut, Ctrl-Shift-P, right? And we'll type Docker add. And there are two options here, Docker files or Docker Compose files. So we haven't looked at the Docker Compose file, so let's select the first one, Docker files. The extension hack is asking us about the application platform. So it's a Node.js application, but it can generate Docker files for .NET, Python, Java, C++, Go, and Ruby apps. So let's select Node.js. All right. And next it's asking us where is the package.json file. So here it is. It's at the root of my application. So I'll select this one. The port that the application is listening to, 3000, perfect. And do I need the optional Docker Compose file? No, not at this time. All right, so the extension quickly added the Docker file and also a Docker ignore file and also a folder for VS Code. So let's take a look at the Docker ignore. Basically, it's a list of files not to deploy in our container. And the Docker file has been created for me. It uses a node base image. It copies everything into the container, the image, and expose port 3000. Perfect. So let's now build this image. So we'll go back to the command palette, view command palette, Control-Shift-P, and this time we'll search for Docker build. All right, here it is. Docker images, build image. All right, so I just issue the command and look at what's happening. The extension is not a black box issuing some crazy or strange commands in the background. It's just issuing a Docker build command here. And remember, a few seconds ago, I mentioned that the name of the application in the package.json file is important. Well, that's the name of our application here. So the extension use it to generate the name for my image. All right, it's just a Docker build command, nothing fancy, but using this extension is a great way to learn about some commands that you may want to use at a later time from the terminal prompt. Okay, terminal will be reused by task. Press any key to close it. Let's press any key. All right. The image has been built. Let's run it now. So view, command palette. Okay, Docker run. So we'll use the first one. And there's a list of my images. And here is my Express app. Perfect. Let's run that. Select image. That's the tag latest. Perfect. And look at what's happening. Docker run -d -p for the localhost port 3000 to the port that the container is listening to. So nothing fancy here. It's commands that you can type yourself, but the extension do that for you. So if I start my browser, localhost, and I go to port 3000, there it is. So that worked. Perfect. Let's now close this. Let's now use the UI provided by the extension. So in the left menu, let's click on the Docker icon here. And from there, you have a list of the running containers, the images, and the different registries that you are connected to. All right, so here's our Express app, my Express app, latest, and its running name, the instance name is called magical_direct. Why so? Well, when we issued a Docker run command using the command palette, the extension didn't provide a name, so one was generated automatically by Docker. So from there, I can view the logs, attach shell, inspect, open in a browser. So if I select that, there it is. That's my app, listening on port 3000. I can stop it, restart it, remove it. So let's remove it here. So are you sure you want to remove container? Yes. It's not in memory anymore. It's not running anymore. But if I look at the list of the images that I have, Here it is, my Express app. So I can right click on it and I have a few options. I can run it, inspect it, pull, push, tag, and even delete it. So let's run it. Okay, and you see at the top, my Express app, and look at the name, gifted underscore El Bakian. Because if you inspect the Docker command that was issued by the extension, there's no name provided. So Docker generated one for us. All right, so let's close this. We can stop or remove it from memory. And if we no longer need the image, we can just remove it here. Are you sure you want to remove the image? Blah, 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 blah. Okay, let's remove it. And it's gone. So what's happening in the background is that the extension is simply issuing a Docker remove image, RMI, to remove the image from this. So nothing really fancy. The extension is not a black box that is issuing some strange commands. It's just regular Docker commands. But I really like the UI provided here. And so instead of typing, okay, let's try this. Let's clear this and let's type Docker images. Here's a list of all my images, but here I have a nice UI listing all the same images here. So sometimes it's easier having a little UI to help you accomplish some task. Other times it's easier issuing the commands from the terminal or the command prompt. So it's up to you. You can use the UI or the terminal. Let's talk about data persistence. Containers are ephemeral and stateless, so you don't usually store data in them. Of course, you can write data in a container, but if you destroy one or if it crashes, any data stored in it will be lost. So it's okay to write some log files or scrap data that you don't want to keep, as long as you understand that you will lose these files at some point in time. To persist data, you need to store it outside the container in what we call a volume. A volume maps an external folder or even a cloud storage service to a local folder inside your container. So your app sees a volume just like any regular folder. The O's in this diagram represent the server or the virtual machine where the container is running. As you can see, a local folder is mapped to the VM file system, so data stored in a volume will survive a container restart or crash. There's still a chance that we can lose the data if the VM crashes. So later on, we'll see how we can use some type of external storage provided by the cloud provider. But first thing first, in the next lecture, you'll see how to create a volume that maps to a VM file system. And this concludes this lecture on data persistence. Let's see how to create volumes. Here's a cheat sheet listing the Docker commands for managing volumes. Docker create volume will create a new volume. Volume ls will list all the volumes. Volume inspect will get you information about a volume. Volume remove will delete a volume, destroying all the files stored in it. And volume prune will delete all the volumes currently not mounted or not in use. So be super careful using this command. All right. You first need to create a volume using the docker volume create command. Then, when you run a container, you need to use the vSwitch, or the volume parameter, specifying the volume name, a colon, and the name of a local folder. That folder will be a logical folder in your code. So your code will see it just like any regular folder. If you use the inspect command, you'll see the logical folder location in the VM. Instead of using a volume, you can specify a local folder. This is great for testing purposes. Let's say you started developing a service and that you want to test on your dev machine if your code can read and write some files correctly. You can use this kind of mapping, but don't use that in production. Using the inspect command, you can see the local folder path. And this concludes this lecture on volumes. Let's now persist some data outside of a running container. So to do that, we'll use a volume. So I'll open a terminal and we'll use the docker volume create and the name of the volume. So this will create a volume. Perfect. Let's now list the volumes on my machine. So there's a few here. The first 4 were created earlier. This is the volume that we just created. Now let's run an Nginx image and let's attach or map a local folder to that volume. So we'll use docker run -d for detach. We'll name our instance vol-test. With the -d for volume, we'll use the volume name that we created earlier and map that to a folder called app on our Nginx image. All right, let's do that. Okay, excellent. So that worked. Now let's connect to our running instance. So docker exec -it, the name of the instance, and we'll run bash here. Perfect. Let's first do an ls to see if we see the app folder. There it is. So that folder is mapped to the volume. So anything that we store or write in that folder will be written externally outside of the container. So that will persist. All right. Just for fun, instead of doing a cat, let's install Nano inside the running instance. So I'll do first an apt-get update. Remember, this is running inside the container, and we'll install Nano apt-get install Nano, which is a small editor. Perfect. I'll cd into the app folder and open Nano. So Nano, and we'll create a file called test.txt. Hello volume. All right, and we'll use Control O to write to disk. Control O, enter, and Control X to exit Nano. Perfect. If I do an ls here, I should see my file. There it is, test.txt. So let's exit the running instance. And what we'll do, we'll stop the running instance and we'll remove it from memory. Stop it here. And we will remove it from memory with rm. Okay, so now the container or the instance is gone. If we would have stored some data inside that container, it would be lost at this point. But we use a volume, so the data was stored externally. So let's try to create a second instance. Same thing, using the same volume, and let's exec to it. Perfect. Let's see what is in the app folder. Here is our file. So let's do cat test.txt just to prove hello volume. That worked. Let's exit here. This proved that by using a volume, your data persists, a container restart or crash here. The data is still there until I remove the volume. So if I issue a Docker volume remove and the name of the volume, you see, it doesn't work. Why? The error says that the volume is in use. Interesting. So I need to stop any container instance that is running and remove it from memory before deleting or removing a volume. Let's try again. Docker volume rm for remove my volume, and this time it worked. Now, another thing I want to show you, let me create it again. Perfect. And let's switch to the Docker UI here. If I click Docker here, there's a section that lists the different volumes here. So my vol is listed here. So here I can inspect. I cannot look at the files, but I can manage it. So I can click here on remove. That will delete the volume. Are you sure? Yes. Let's now see the YAML concepts. YAML stands for YAML Ain't Markup Language. It's a way to serialize data so that it's readable by human beings. It's the file format used by Docker Compose and Kubernetes. Here's a sample YAML file. For a key value pair, you specify the key, a colon, then a space, and the value. Don't forget the space, it's mandatory. Here are some nested values. You specify child values using two-space indentation. And quotes are not needed for string values. Here's a list. Again, the child elements are indented with two spaces, and there's a space after the dash. This is what we call the block style. There's also a flow style that looks like JSON. So you may be tempted to use it if you're familiar with JSON, but don't. I never saw any sample or any documentation using this flow style. Since it's easy to forget a space, and you can spend quite some time figuring out why your YAML file doesn't work, you can use tools like this linter available on yamllint.com. It will parse your YAML and flag any errors. Very useful. And this concludes this lecture on the YAML concepts. Let's now take a look at the Docker Compose concepts. Let's say that your app is composed of multiple containers. You run the front-end container using a docker run command, docker run again for the backend container, and again for the Redis cache container. So you end up issuing multiple Docker run commands to run your app. Would it be nice if you could deploy your app using one single command? Well, that's the Docker Compose goal, to define and run multi-containers application using a single YAML file. There's a Compose plugin that extends the Docker CLI and lets you run those Docker Compose files. The specifications are available here. If you looked at Docker Compose before, you may have seen that sometimes the commands are using an hyphen, so docker-compose, and sometimes they do not. Why is this? At the DockerCon conference in 2022, Docker announced the general availability of Compose version 2. Okay, this means that there was a V1 before, and the V1 command line tool was installed separately from the Docker CLI. It was built using Python, so you needed to have Python installed to run Compose V1, and the syntax was docker-compose. Compose V2 is a drop-in replacement, meaning that all the V1 commands are working as expected. It's installed as a Docker CLI plugin automatically by Docker Desktop. To use it, you type docker space compose. No hyphen needed here. It's written in Go, so no need to have Python installed to run the command. In summary, it's simply a faster version of the Docker Compose tool shipped as a Docker plugin instead of a Python application. Here's a Docker Compose file. There are 3 containers defined in it: Web API 1, Web API 2, and API Gateway. The name that you use here defines the network or host name for that container. The code running inside your container can use these host names to communicate between each container. For each of them, you specify the image to run. You set the internal and external port the container will listen on. Note that the API version is now optional, so it's okay to skip it. You may ask yourself, should I use Docker Compose or not? Docker Compose is perfect for small workloads that don't require a full orchestrator like Kubernetes. It's perfect when developing and testing locally before deploying to Kubernetes. Some cloud providers offer services that support Docker Compose, like App Service on Azure and ECS on AWS. And of course, you can simply use a virtual machine or a VPS, virtual private server, with DigitalOcean or Linux. And this concludes this lecture on the Docker Compose concepts. Let's now use Docker Compose. Here's a cheat sheet listing some of the Docker Compose commands. Docker Compose build lets you build the containers as defined in your Docker Compose YAML file. If the file is located in another folder, you can use the optional -f parameter and specify the file's location. Start will start all the containers as defined in your YAML file. Stop will stop them, but they'll remain in memory. Up will do a build followed by a start. This is super handy. Use the -d parameter to run the command in the background and take back your terminal prompt. PS will list what's running. Remove or RM will remove the containers currently from memory. Down will do a stop followed by a remove. Again, this is super handy. Logs will display the logs for a container. And you can open a session inside a container by running docker compose exec, the container name, and the program to run. The Docker Compose file is located inside a folder. And if you run Docker Compose up, this will launch your application. If you try to run Docker Compose up a second time from the same folder, nothing will happen because the application is currently running. If you want to run a second instance of your application, it was impossible with Docker Compose v1. But with v2, you can use a project name to launch a second instance of your application from the same folder. Here's a cheat sheet for some of the new commands. Docker compose -- project -name followed by a project name. This will run an instance of the application as a project. The shortcut is much shorter to type. -p instead of -- project -name. You can list the project currently running by using compose ls. CP will allow you to copy files from the containers. So this is super handy to retrieve, let's say, log files. And you can copy files to the container. So from your machine, your desktop or laptop, to the container by using Docker Compose CP, the source path, the container ID, and the destination path. Here's an example. Imagine that the Docker Compose file is located in the same folder where you run these commands. You simply use the up command to build and run the containers. And to take them down, simply use the down command. And this concludes this lecture on Docker Compose. In this lab, we will deploy a Docker Compose application. Let's take a look at our Docker Compose.yaml file. We have one section called Services, and under that section, we define two services. The first one is called web-fe, FE for front end. It's a Python application, and instead of using an image from Docker Hub, we'll be building that image using the build parameter. The dot means that the Docker file is at the same level as the Docker Compose file. So here it is. It's a simple Python application, just one file, app.py, and requirement.txt that we're copying on that base image. It will be listening on port 5000, and this is our second service. It's a Redis cache, and this time we'll be using an image from Docker Hub. All right, let's open a terminal. And let's build the image using Docker Compose build. Perfect, my image was built. Now I can launch the application using Docker Compose up and -d for detach. Now I could have skipped the build step because up does a build first and then a start. So it's super handy. So let's use Docker Compose up, and my application is up and running. I can test it. If I go to localhost 5000, you visited me one time. I'll do a few refreshes. 5 times, perfect. Okay, I can list the running containers using Docker Compose PS. I can also use Docker PS since it will list the Docker container currently running. And I can look at the logs for my front-end service using Docker Compose logs -f and the name of the service. And if I move that a little bit and hit F5 a few times, you see, new entries are logged. Perfect. That works. Let's do a Control-C to terminate the log streaming. And we'll use Docker Compose ls to list the currently running projects. I have one project running. It's called L09-04 Docker Compose. Well, basically, when I use Docker Compose up, I didn't specify a project name. So Docker Compose used the folder name as the project name. Now let's try to create a second instance of our application. If we use Docker Compose up-d again, well, Docker Compose tells me that the application is running, so it will not start a new version. We can try to deploy our second version using a project name. So Docker Compose -p for project name. We'll name it test up-d. Let's see what will happen. Starting. Oops, we have an error here. Bind for localhost 5000 failed. Port is already allocated. Of course, my localhost port 5000 is in use right now. So what I need to do, I need to change that port here, the localhost port. I'll use 5001. Save the file and use the same command, Docker Compose -p project name test up-d. And this time it worked. Awesome. Let's open our browser and let's go to port 5001. Yes, that worked. A few refreshes, 10 times. Let's go back to port 5000, the first instance, 15 times. All right. So let's do a Docker Compose ls again to list our projects. Now we have two projects. The first one that we deploy without specifying a project name, and the second one with the project name test. Let's delete our first instance by using Docker Compose down. So I didn't specify a project name. Docker Compose used the folder name as the project name. Now, if I do the Docker Compose ls, I should have only one project running. Yes, it's test. Now I can delete that one using Docker Compose, specifying the project name, and down. Let's list the projects again. Docker Compose ls. Nothing running. PS. Listing the containers. Nothing. And why not try Docker PS? Nothing in memory. In this lab, we will deploy a Docker Compose sample application that is composed of 3 services: a web front-end built with React, a Node.js backend, and a MariaDB database. Let's take a look at our Docker Compose file. This is more complex than what we saw so far, so let's try to break it into smaller pieces. Here we have the definition of our 3 services. If we start from the left, we have the backend service. Top right, the database, DB, and the front end. Now, if you look at the DB service, you can see that we're referencing an image that will pull from Docker Hub. And the other 2 services, we're using the build parameter. This means that we will build these two images. Looking at the backend service, we can see that we specify build and context. Context with the value of backend. Backend is actually a subfolder where the Docker file is located. Next, we're defining two networks, public and private. We can see that our front-end service is using the public network. The back-end service is using public and private. And the database service, the DB service, use only the private network. Front-end being in the public network cannot communicate directly with the DB service. But backend, being in both public and private, can communicate with both DB and front-end services. We're defining also two named volumes, backend-modules and db-data. And we can see highlighted in yellow that our DB service is using DB data and our backend service is using backend modules. Highlighted in yellow, we also see that we're using other volumes. These volumes are scoped at the service level and are not shared between services. To create an instance of our Docker Compose application, we simply use Docker Compose up, and to bring it down, Docker Compose down. In Visual Studio Code, let's take a look at the Docker Compose file. So it's called compose.yaml. Here we have our services section, network section, where we define two networks, the name volumes, backend modules and DB data, and secrets that we haven't seen yet, where we're defining one key value pair. So the key is DB password, and we get the secret from a file. The file is located in the folder called DB, and it gets the value from a file called password.txt. If we open the DB folder, here's the file with the value, the secret. And that will be injected when we run Docker Compose up. Okay, let's go back to the services section. And here we have our backend, DB, and front-end services. Let's take a look at backend. We're using the build directive, and we are setting the context to backend. It points to this folder called backend here, and the Docker file is located inside that backend folder with the application. Same thing with the front-end service, build, context front-end, and we're getting the Docker file and the application from the front-end folder. And what about the DB service? Well, we're using an image that will pull from Docker Hub. Okay, let's build our two images. We'll open a terminal and run Docker Compose build. Our images were built. Perfect. Now let's run the application by using Docker Compose up-d. Perfect. The application is listening on port 3000. So let's open a browser and type localhost 3000. Here's our React application. It's working. Awesome. We can list the containers that are currently running by using Docker Compose PS. We should have 3. Backend, DB, frontend. Awesome. Let's take a look at the logs from the backend service, Docker Compose logs-f backend. And these are the logs for our backend service. Awesome. We can type Control-C to stop the log streaming. And we can take our application down by using Docker Compose down. This will stop and remove the containers from memory. Do we have something else in memory? We should not. Perfect. Even if I type Docker PS, there's nothing. However, the volumes are still there. When you do a Docker Compose down, it will remove the containers from memory, but will not remove the volumes. So if I open the Docker desktop application and I click on volumes here, I can see that I have three volumes that were created a few minutes ago. So I need to delete them manually. I can select them right here and click on delete, or I can do the same thing by clicking on the Docker icon in VS Code, locating the volumes here and delete them. Find it easier to do that in Docker Desktop because we see when the volumes were created. So I'm pretty sure that these three are the ones that I need to delete. I'll click on the delete button and confirm. Let's take a look at some of the Compose file features. It's a good practice to set limits on the resources that your container will use. In this example, highlighted in yellow, we tell Docker to start the container with 1/4 of a CPU and 20 megabytes of RAM. The green section is the limits that we are allowing. In this case, half of a CPU and 150 megabytes of RAM. To set an environment variable that will be injected in the running instance, simply set the key value pair in the environment section. Those values can be overridden at the command line using the -e parameter. You can reference an environment variable using the $curly bracket syntax. This way, you can set the variable on your machine or server and use it directly in the Compose file. You can place the values in a file that you'll name .env, located in the same folder as the Compose file. The Compose command will automatically read the values from that file. By default, all containers specified in a Compose file will see each other using their service names. Here, we have two services, web and DB. The code running in the web service can communicate with the second one using DB as the host name, and vice versa. The web container is visible from outside of the Docker network using the port number configured in the left portion of the port's value. Web is listening inside the Docker network on port 80. DB can reach web on port 80. Finally, DB only exposes one port number. That's the internal port. Web can reach DB using port 5432, but DB is not visible from outside the Docker network. If you have a Compose application with multiple containers, you can restrict who sees who by configuring networks. In this example, we're defining two networks, front-end and back-end. Proxy can see app because both are part of the front-end network. However, proxy does not see DB because it's not part of the backend network. When using multiple containers, you may want to start some of them first and wait until they are running before starting the other ones. A typical use case is a database that you want to run before starting the main application. Doing so is easy using the depends on parameter, where you simply specify what is the service name that the service is dependent on. In this example, app depends on DB, so Compose will first start DB, and when DB is running, Compose will then start app. You can declare volumes in the volumes section. These are called named volumes, and they can be used by all these services that you are declaring in the Compose file. To use a volume from a service, map it to a local folder using the volume name, colon, and the virtual path inside the container. Optionally, you can make the mapping read-only by appending colon RO to the mapping. You can also create a mapping without using a named volume. This mapping can't be shared across services. It's also a good practice to set a restart policy. Let's say that you deploy your Compose app in a VM, and at some point you need to install some OS patches, and you need to restart or reboot the server. What will happen to your Compose app? Well, if you don't specify a restart policy, the one by default is no, meaning that Compose will not restart the containers if they were shut down by reboot. You can set the policy to always. This way, Compose restarts the containers until their removal. On failure, restarts a container if the exec code indicates an error. And lastly, unless stop does a restart unless you stopped or removed the containers. And this concludes this look at some of the Docker Compose features. Let's now talk about container registries. So, what is a container registry? It's a central repository for container images. You build an image locally, then you push and store the binary, the different layers, to the repository. They can be private or public. The default one is Docker Hub. Microsoft, AWS, and Google each offer container registries as a service. The benefit of using a repository from your cloud provider is that the images are located near your app, so no hops over the internet to retrieve the images. So let's say we want to retrieve an image from Docker Hub. We issue a Docker pull command, and Docker downloads the images layers and store them in its local cache. And this concludes this lecture on container registries. Let's see how to push and pull images to Docker Hub. Make sure you are logged in with your Docker user account. To be sure, simply type Docker login without a username and password. Docker will tell you that you're already logged in. If not, enter your Docker username and password. You need to tag an image with the repository name. By default, it's your username. If you have created some organization in Docker Hub, prefix it to the name of the image. In this example, I want to push this image to my Kate's Academy organization. Then, use the push command And don't forget to specify the organization name. It's part of the image name. To retrieve the image, we use the pull command with the image full name. On Docker Hub, public images are available for download to anyone. If you don't want to share them, you need to create a private repository. Later on, we will create one using our cloud provider. And this concludes this lecture on Docker Hub.